Good evening to all. I am Imtiaz Ahmed Shah from Professor Kim Jong-un Lab. I am enrolled as a third semester. I want to give you presentations about my coursework MMIC technology. MMIC. I want to give the presentations of the chapter 2 gallium indium gallium phosphate and gallium arsenide HBT heterojunction bipolar transistor Foundry from our beloved Professor Namiam King book, MMIC technology books. So first I want to discuss about the contents. Here in this chapter lots of contents are there. This chapter actually contains the Foundry service and process of manufacturing MMIC. First I want to introduce the introduction to Foundry service, then indium gallium phosphate and gallium arsenide HBT process, heterojunction bipolar transistor process sequence to fabricate BGT IC flow diagrams, some active device indium gallium phosphate and indium gallium phosphate HBT devices, BBIC models, extraction of parasitic elements, that is parasitic elements we call capacitance, extractions of parasitic elements inductance, extraction of intrinsic elements, extractions of DC model parameters, extraction of AC model parameters. AC means direct current, alternating current, and DC current model parameters, passive devices, layout and design. In the last I say the concrete design layout and DRC design rule checkups, how to check the error. So these all are the contents of my presentations. So let's go introduction to the Foundry service. This chapter actually contains all the topics about fabrication techniques and how to manufacture, how to produce the MMIC technology, and how to make chip layout. All the things these are called, first we call this is Foundry process. Foundry means factory or fabricated process. So from that structure we see all the process from initial stage to final stage they mentioned here. This one is our first stage, where this one is our circuit diagram. We design some software, that is ADS, Keysight ADS. From Keysight ADS, this software we usually use this software as our gallium nitrate or gallium arsenide like IC design activities. And then this is our schematic diagram. Then we design the layout, PCB layout diagram. Then PCB layout diagrams we simulate this. After simulation we design the PCB layout, and then we go to the some design rule checkup error, and then design Foundry process also they are checking the design rules error, and then there are some process receive generation techniques, some documentation they did, and then or before fabrications after fabrications we actually test the IC with probe stations and evaluate and give the evaluation form of the customers. Here in the Foundry service process, maximum customers are use multiple project wafer applications, and before fabricate or before to design we need a agreement. This is company to customer agreement, and this is NDA submissions. Before fabrication we need to start, and also we need to sign up this agreement, and RSR is then verified the informed and due date, and design kit received to the company. The overall MMIC and fabrication process are depicted in the Foundry service figure, and through the PCMC process control monitoring, both customer and company know if anything goes wrong to this process. This is the overall Foundry or fabrication process in summary view. So indium gallium phosphate and gallium arsenide HBT process. Here I mentioned 6-inch HBT process from the initial stage to the last stage with a flowchart diagram. if we start here from, this is emitter content, emitter isolations, then basic contact, second nitrate, first base pedestal, like this, then collector, then fourth nitrate we need to go, and preservations. And this is the schematic layout of indium gallium phosphate and gallium arsenide heterojunction bipolar transistors. Here is the emitter contact, emitter cap. We know heterojunction bipolar transistor from that. No, we know that this is actually transistor. Transistor are created with NPN or PNP transistor. So in transistor there is three part. There are three part. These three part are actually called as the emitter, base, and collector. So here we put emitter cap as a gallium arsenide. Emitter N-type material we put indium gallium phosphate. In base station we are using gallium arsenide and collector. In collector, in N-type materials, gallium arsenides are mentioned here. Sorry for I have a check. I need to check the camera. First each part is need to patterned, and second evaporations, lift off, and etching deposition process also are there. In the third you need to final passivations, and final passivation process remains in this stage. So we can go next slide. Next slide also. Also the flowchart I extend here. Here we need to, from the back side flowchart, what we need to do. Sapphire wafer bonding. Wafer means we need to put silicon, some substrate materials on the metal. This is wafer. In the back side we need to put via in this IC design, and then and metallizations in the middle we need to put back side scrape straight also there, and sapphire wafer demount we need to do in the last end, and scrape the baker. This is the back side of the 6-inch HBT heterojunction bipolar transistor process. So some there is some active device or passive device. In indium gallium phosphate or gallium arsenide there is some active device. This is characterized. This is actually important, play a role in characterization of amplification and non-linearity. Requires DC bias. DC bias sums we put transistor diode HBT, and group 3 to group 4 group 5 HBT break the link between N and beta. Beta we know this is a constant. There is a relation of beta, alpha, beta, gamma also there. We know there is a relation with beta, means IC divided IB. Have a heterostructure, high electron mobility and velocity. They are based on the substrate of gallium arsenide, high resistivity. Heterojunction process band gap difference between emitter and base. Previously I told that there is a three part of transistor: emitter, base, collector. So it is actually heterostructure junction remain in between the gap between the emitter and base. Has a higher emitter injections efficiency, high current gain to homojunctions. This is the actual cross-sectional view of indium gallium phosphate and gallium arsenide HBT structure. HBT device, indium gallium phosphate and HBT devices. Actually the high linearity ACL process active devices. Group 3 and 4 HBT are based on the substrate of gallium arsenide materials and high resistivity. The system has a higher emitter injection efficiency and higher current gain than the homojunctions. Once the current gain, the other is a base emitter voltage. If one sector is remain as a current gain, other section will remain as a base emitter voltage. This is our indium gallium arsenide contact. All the cross section view I mentioned here: emitter, base, collector, sub collector, substrate. At the bottom layer you need to put gallium arsenide substrate. So some modelings are also there, how to set up, how to do layout, how to design. This is actually called modeling. In modeling, parasitic, intrinsic, DC, AC parameters are required to assess the perfect model. AC and DC voltage source, we need to give this modeling sectors. Actually we need a measurement PC. From measurement PC we using the software ADS, Keysight ADS. From Keysight ADS we design actually silicon type of IC. Then we need to give some network analyzer, measurement hardware tool, network analyzer, signal analyzer, signal generator, spectrum analyzer. From a spectrum analyzer we need to measure. This is actually probe station. Probe stations this is so nano type IC, so it is so small. So probe station need to see the how the structure layout in how the structure laid in the IC chip, and from probe station we need to measure the data and again give to the PC. So I tell all the scenario in a nutshell. So this is a BBIC model extend to improve the efficiency of SGG model, is still based on Gamel-Pon formulations, but it improved the many effects and selectively based on model and parameters value. The model includes the intrinsic BGT, NPN, bipolar transactions. Parasitic BGT is PNP type, NPN, and another is PNP. So P type material and N type materials actually modeled with a partially SGP model. The contents characteristics CBO, EO, CBOC, CO are included in the model. Extensive parasitic capacitance. Extraction of parasitic elements. Parasitic actually used as a capacitance, as a inductance. This is actually from that figure we see that this is actually T shape, and we use two capacitor CP1, CP2. These are actually a parasitic capacitance. Parasitic capacitance are extended by opening patterns, and these figures are shows. Actually, this is our probe station view. From probe stations we see this is the so micro nanometer line are design, and this is the photographic open pattern, equivalent circuit of open pattern, and the HBT model is small signal equivalent circuits. T model we put all the capacitance with resistors, and here in the series we add inductance with resistors, and in the parallel with resistor with parallel we give connection with the resistors. So extraction of parasitic elements. Parasitic capacitance HBT models is a small signal equivalent circuit as shown in figure, and the parasitic capacitance in the input and the output in the ground, it should be capacitic capacitance. It is also called decoupling capacitor. Decoupling capacitor is connected like in parallel, and they are connected as a ground, and figure shows the photographic equivalent circuit of the open patterns. The parasitic inductance are extracted by the short patterns. The LE, LB and LC indicates the parasitic inductance. Parasitic inductance also connect here. Inductance we know the loop of coil. This is actually inductance, this is capacitance. Extraction of intrinsic elements. We know that two elements we need to add with as a impurity, that is intrinsic, intrinsic, and another is extrinsic. So intrinsic elements are resistance. We know when we measure the RF radio frequency, there is a parameter. This is called S parameter. In the intrinsic S parameter is converted and obtained above the de-embedding process. The whole instructions of parameters are carried out using these extrinsic S parameters. The resistance value is determined the average resistance in sorry for camera. Resistance in flat frequency regions. This is emitter resistance, this is base resistance, and this is collector resistance. From here graph we see that this is actually collector resistance, this is circle shape is base resistance, and there is also square shape, this is called emitter resistance. We take this graph as against with frequency and resistance. Another option I told that previously, extraction of intrinsic elements. There is a thermal resistance. We know temperature also effect on our layout. So we are used IC. IC remain in the core of the PCB board. So it consumes lots of heat. So for that case, we need to mention as a intrinsic elements intrinsic element as a thermal resistance. The accuracy of thermal resistance is important factors. The thermal resistance is defined as the rise in the junction temperature above the temperature of the reference point and measured 25, 50, 70 to 100 degrees Celsius is shown in figure below. There is a method of Padova method. Padova method is used where this is called voltage B, collector emitter voltage, collector current, base emitter voltage, and base current. Then we get P dissipations value. From P dissipation value we calculate the RTH. RTH means thermal resistance. This is actually beta A, beta B. From this calculation we find the thermal resistance of this component or IC. This is the IV curve of, we are everybody famous about semiconductor. There is a IV curve. IV curve is used as a transistor. In a we put the IC current, collector current against collector voltage. So extraction of the DC model parameters is GaML plot. The DC parameter of the base and collector currents of the HBT are determined the GaML measurement. DC parameter, DC direct current parameter, that means base and collector current, IC and IB determine the GaML measurement. The forward GaML plot shows the base current and the collector current with the same voltage applied to the both base and the collector. The reverse GaML plot presents the base current and emitter current with the same voltage applied for both emitters. This is the forward GaML plot, and this is the reverse GaML plot. Actually, this is the relation between the base and collector. So extraction of the DC model parameters, I previously told previous slide that IV characteristics curve is more important in transistor N-type or P-type materials. From IV curve actually we understand how much current after how much current consuming it goes to saturation state. So this is actually saturation state and this is the current consuming. This is our voltage, collector emitter voltage. To extract the RCI to optimize the offset voltage, when the current goes to saturation stage, this is the called offset voltage. All are offset voltage. So here offset voltage is 0.5. To optimize the RE control current and extractions, XIN, XI controls the slope of the curve, and it is necessary to use IV curve with a constant voltage. Extraction of AC model. AC junction capacitance. We know the capacitance means it is actually connected with parallel. In capacitance we calculate the impedance. Means impedance we know Z equals to 1 by J omega C. So when we talk about any connection in AC signal, we just at that time we need to remember the capacitance. Actually capacitance did not carry the DC voltage. Capacitance actually carry the AC current. Junction capacitance I mentioned here. The base collector capacitance is very important in determining the AC performance of a bipolar transistor. The extraction method of base collector junction capacitance and base emitter junction capacitance are shown in these equations. This is the tangent time parameters equation. There are 4 types of parameters with respect to the tangent value and VBIC models. Some previously I discussed about the active device. Now come in our presentation topics. This is passive device. Resistor also called as a passive device, and resistor of in an MMIC can use a doped semiconductor layer and deposit in a thin film resistive layer. The material of resistor is a nickel chromium thin film. The saturation thin film resistors offer improve the linearity, lower temperature coefficient in comparison to that others, and sheet resistance of 50 ohm and square can be produced, and which is the convenient to circuit designer. This is the resistive configurations. And via and pad also play impact role in a design. Via we need to put to connect top to bottom layer as a ground, so that our PCB remain strong. Also we need to remove the resonance through by connections via. We can remove the resonance. The backside via holes are used to connect the device RF circuit, radio frequency circuit on the front side and metallized backend, and via holes can be needed to RF device in a single port, and from the fronted pad backside ground. And this is some passive device spiral inductors. Actually inductors also is related with AC source, AC signals. Inductors actually loop a coil, and in MMIC design we need inductors. We need to put inductors. Actually the loss is we are using spiral inductors. I already told that the inductor looks like a spiral coil and has a high Q factors, gap between the inductors, a gap between the contour of the microstrip and post always 0.5. Spacing between the ER bridge first is different. All cases 2 types E and PA, power amplifier type here. This is the reference plane of MMIC capacitor device. MMIC both overlay capacitor and inter-digit capacitors can be used in MMIC. Most popular is MIM capacitors, and DC block and MASIC section or blazing circuitry are widely utilized these components. This is the layout design. Layout design rules. In when we are go for designing, there is a first we need to draw the schematic layout, then simulations, then we can design the PCB layout design. Then this is actually a layout of design MMIC. This is PCB layout, and for PCB MMIC fabrications, monolithical microwave IC integrated circuit fabrication process, the manufacturer design to manual, the essential authority to exact design rules, and the maximum stepping tile size on the wafer, and the maximum width and height of the chip are both restricted to 15 nanometers. Interconnected metal sheet IMS. IMS layer is a patterned before sputtering or sheet metals of our electroplatings. Minimum surrounding FNFV IMS 0.2 micrometer, and the non-active device area, and minimum spacing between IMS and IMS, this is 0.3 micrometer. And last we can say the design rule check. So when we are design at that time we need to cross our DRC rule. If we pass the DRC rule, then we can satisfy that if our designing is good or it is wrong. For every case, when we put anything in a layout design, so we need to pass the DRC. DRC nothing but is actually the rule for checking error checking. So it is important to check all the part designed and confirm the manufacturer specification meet. Among 2 types of DRC, quick check patterns, minimum width and spacing. Quick case that is less checking, and In maximize, when the take times, it check all the things at a times. So this is actually we are checking for error. So this is the end of my presentation. So this is the actual all the things scenario I described in chapter 2. So thank you all. This is my end presentation.